Yeah, except Andrea is not from Montreal, but whatever. Anyway, so first up, why do we need a new common GPU ND-array thing? The first thing is that efficient linear algebra is at the core of many, what? The mic is what? So, as I was saying, efficient linear algebra is at the core of many applications, especially in machine learning, but also in other domains in science. And on the CPU, in Python at least, you have a NumPy that provides the ND-array object, which is a standard matrix, tensor, multidimensional thing, which allows sharing code between projects that use this as a basis for their data. There are already on the GPU a number of implementations that work some kind of tensor object, resembling the ND-array and NumPy. The Tiano code base has one, PyCUDA and PyOpenCL also, CUDA-Math, NumPy, Trust, all have some sort of GPU ND-array object. But all of these are incompatible, so it kind of renders code sharing difficult because you have to convert the data representation and underlying object whenever you want to port a kernel or something from one code base to the other. Also, none of these implementations support the full range of ND-array features. They typically concentrate on a sub portion of features which is essential for their work or easy to do because some parts are harder than others. And as a last point, none of them support both CUDA and OpenCL with the same code base. And actually only PyOpenCL supports OpenCL of all of those. So, what do we want as features for a new basic object? The support for varying data types, I mean not only floating point, single person, but also integers, globals, and complex if possible. Also support for an arbitrary number of dimensions, which is because some algorithms require more than one dimension, well, more than 2 or 3 dimensions to implement a convolution. If you say you have a tree convolution and then some number of examples, then you need 4 dimensions, and it's really a pain to do if your basic object doesn't support that. Also support for strides. Strides, for those who might not be familiar, is a way to specify how much memory to skip between each element in a dimension. So say you have a big matrix A in pink here, and you want to take a submatrix of it without copying data. Then you can say the dimension of the matrix stops here, but the stride for the rows goes up to here. So that way you can access only the subportion in blue, while still not copying any data and using the same stacking sort for both matrices. Another feature that is useful is broadcasting. This is a kind of a computational trick to ease some operations, like when you do like a neural network implementation, you want to add a bias vector to a matrix of examples. You have, say, the big red matrix of examples and the blue bias vector. If you do a usual element-wise operation like that, like an addition, it won't fit the rules because there's less elements in the vector than in the matrix. So you would have to do something else, which is to make virtual copies of your vector so that it is kind of the same size as A, and then you can proceed as usual. But one thing here is that these copies are not actual in-memory copies. It's just virtual copies made with a trick on Stride to make it seem as if the elements repeat. And the last point we want is support compatibility with CUDA and OpenCL to be able to share code, hopefully, between these two platforms. Okay, so why has this not been done before, actually? The first point, and probably only the only one, is that it's hard and time-consuming to get right, and also efficient at the same point. Because even if you support everything, but it's really, really slow, then nobody is going to use it. And the main sub-point of that is that the indexing computation, when done on GPU, take up a significant portion of time compared to what they would take on the CPU. But at the same point, even if we want to support everything and have strides and whatever, we don't want to be this thing to be hard to develop for. So if you're writing a kernel and you don't want to support generic strides or whatever broadcasting because it's harder to code the kernel that way, we provide the convenience function where you can just call as contiguous or Fortran memory, and then you have your input copied in a Fortran or whatever order, and then you can just assume it's contiguous for the rest of your kernel. Okay, this is a comparison of the supported features for all implementations. Well, not every implementation under the sun, but those we found. And you can see there that the strides and broadcasts are pretty much only supported by Piano. And since it's much easier to add more types than to add strides to an implementation, we started with a Piano code for our thing because it better matches the bottom line, which is what we want. So what we have right now are data types. We support all sorts of data types like integers, float, doubles, whatever. Any number of dimensions, strides and views, broadcasting, element-wise kernel, some support for reduction, but it's not complete right now. And we support all of those on CUDA and OpenCL. We also have a Python interface and a C++ interface, which is similar to the NumPy C API, but depends on Python. This will have to be cleaned up because we want to be able to use this not only in Python, but probably in Ruby, Lua, or Torch, or something. We are missing currently assignation of a submatrix or elements, but that's not too hard to add. Reshaping of matrix and a clean C interface, as I mentioned. Okay, so as part of it's hard to get right and efficient. This is an example of an optimization that we have done to make it complete and efficient at the same time. I said before that indexing computation on the GPU are expensive because you have to compute from an index, which is the thread ID or something like that. You have to compute where you are in memory to get the proper element. And then this requires to do a sequence of module and divisions to get to the element you want. So the cost is paid per dimension. It doesn't matter if the dimension is really big or really small. It's the number of dimensions that matters. So we have an optimization that can help alleviate this cost, which is element-wise dimension collapsing. So suppose you have a 3D thing like that, and the whole cube is a 3D tensor called A, which you could see is pink, and then you have a subtensor B, which is the blue part. And you want to do some element-wise work on that. We can collapse the outer two dimensions, this one and this one, so that they correspond to one single long dimension. Even if it's bigger, since you have one less dimension, it's faster to access memory. You cannot collapse straighted dimensions, so it's that way. And if all of your dimensions are contiguous, you can just collapse all of them to one single long vector and it's really fast. Here are some benchmarks to illustrate that we are not super slow. So blue line at the bottom here is some CUDA kernels doing A+1. So it's just a stupid, really small kernel to illustrate the overhead. On contiguous kernel, which you can derive with one dimension or 4 dimensions, but the 4-dimension one is collapsed back to 1. You can see the red and green line at the bottom, which are really close to the CUDA 1. If you have a 4D thing, but it's not collapsed, meaning you do 4 dimensions of indexing computation, it's the faint blue line at the top that goes really, really up. So you can see that the computation takes a significant portion of time. Even if as you add more elements, it takes more and more time. And if we have a 4D with one strided dimension, so it becomes 2 dimensions after collapsing, it's the purple line in the middle. So there's still some overhead because you have more dimensions, but it's still faster than just not doing anything. So our future plans for this project is to use it in Piano, PyCUDA, and PyQCL. These three are kind of a given because most of the authors of this are also developers in Piano, and we have the author of PyOpenCL and PyCUDA helping us. But we would like to use it in other projects too, or be used. Design and implement a good C or C++ interface, and for that we might need help from some C people if there are some in the room, or you know some guys. Find other ways to lower the overhead, like the element-wise collapsing, but if we can design some new optimizations that would help, it would be good. Use the implicit looping provided by CUDA and OpenCL for faster loops. And finally, world lamination, which is being used in everything everywhere. For that last point, we would ask library authors to come and see us so that we can discuss using this, or supervisors to talk to your students about this project so that they know about it and hopefully use it. I would like to acknowledge James Bergstra because he wrote some of the Piano code we started from, and Compute Canada, RQCHP, and Clark Canada Research for providing funds and access to research while doing the development of this and testing too. So, any questions? Yeah, well, we heard about the similar library yesterday or something. So, yeah.
That's what I understood, but we just learned that the V1 not ago it was existent when we, as we are reviewing paper for the categories, it was embedded some existing paper here. So we want to work with them, and not only one backend.
That's one of the reasons we don't have only a Python interface, because if we have only that, then it would be really hard to work with Torch, for example. So we want a C interface to be able to share. Yeah.
So you syntactically provide either a pointer-based multi-dimensional array or straight collapse without any pointer array. That's the
No, it's
idea.
not a pointer-based array. It's a stride-based array. You remember strides?
Yeah, but
When you're skipping elements in some dimensions, because you save the strides is like 2 elements, and then the real array is 4 elements, gives you only see the first 2 for the dimension.
But in C, there's, normally when you write array, you get these pointer-based multiple dimension array.
Yeah, but it's not. It's actually a big block of memory that we subdivide using virtual dimensions and strides.